Well, hello and welcome back to another episode. It's great to see you all. I hope you're doing well. So today is going to be the first episode of a new series looking at writing a ray tracer from scratch using C++. And for those of you that have been with my channel for quite some time, my longer term subscribers, thank you very much for hanging in there, by the way. You will know that I did do a series on writing a ray tracer in C++ before, which is no longer on the channel because I felt the quality of those videos wasn't really up to the standards that I want to maintain. So I'm very much hoping that this new series will cover that better, and hopefully better quality videos that I'm going to be more happy with and hopefully will be of more value to you as well. Anyway, so in contrast to the previous version of the tutorial, I'm going to be using one additional external library. So before I did writing a ray tracer using only the standard libraries in C++. What I want to do with this series is something a little bit better, because I always felt that was quite limited. It's quite nice if you can actually have a window on the screen and see what's going on. So in order to achieve that, I'm using one additional external library, which is the SDL2 library, which is open source, publicly available. I'll put a link in the description below. You can go and look that up. So to follow along with this tutorial, you will need to install and set up the SDL2 library on your system for whatever development environment that you're using. But the instructions on their website are very good, so simply go and have a look at that, and hopefully that shouldn't present you with any problems. I have only set it up on my Linux system. I don't know anything about doing it for Windows, Visual Studio or anything like that. So just to put that out there, but it is possible, I believe, so you should be able to follow along with that. Also, one other thing I'm going to do, we're going to use vector math, and we're also going to need to use matrix arithmetic. I'm not going to cover writing the code to implement those as part of this series, because that's covered in my previous series on linear algebra in C++. We're going to use the code from the GitHub repository for that library, so that shouldn't present any problems, and you can go back and look at the other videos on my channel from the linear algebra series if you want to know more about how those functions work. Anyway, I think that's pretty much enough of an introduction. We should get into ray tracing. Just quickly before we do, I want to say that if you like this video, please do remember to hit that like button, and if you haven't done so already, please consider subscribing to my channel so you don't have to miss any future videos. Thank you very much. Anyway, before we begin with actually looking at starting to write some code and how a ray tracer, to implement our ray tracer, I think we should have a quick look first at how ray tracing actually works. So ray tracing is a technique for generating 2D images of three-dimensional scenes by mathematically modeling the transport of light around the scene. It has all sorts of applications, ranging from 3D animation, as featured in many Hollywood movies, through to computer games, where real-time ray tracing has become a big thing recently with the advent of hardware capable of delivering that. So in this episode of the series, we're going to take a quick look at the basic principles of how ray tracing works, which we will build on as we go through the series. We will then move on to setting out the directory or folder structure for our project, and we'll write the basic code that is going to form the main structure of our ray tracer. We will end with producing a very simple color gradient image in a window, which will show that although we're some way off implementing ray tracing, at least our basic code structure is functional. Before we can talk about how ray tracing works, it is helpful to consider how a normal camera works, and then build up from there. To make this as simple as possible, let's look at the most basic example, the pinhole camera. So, in this case we have an object that we want to take a picture of, in this case this pink flower here on the right. And we have our pinhole camera, as shown here on the left. And finally, we have a light source of some sort, as illustrated here by the white circle at the top center of the picture. In this situation, light travels from the light source, and some of that light will reflect from the object and pass through the pinhole and into our camera. As more and more light passes through the pinhole, an image is formed on the back plane of the camera. Notice that the image that forms is inverted. Okay, so that seems easy, right? If we just model the rays of light coming from the light source, we can model this process, and that's all we need. Well, no, not quite. The problem is that this process is hugely inefficient. Firstly, a large number of light rays that strike the object will reflect off in other directions and not pass through the pinhole. Secondly, an even larger number of rays emitted by the light source will head off in different directions completely. To produce an image this way, we would have to model literally billions of rays from the light source, and even then there would be no guarantee that we would actually have enough to make a good image. This would obviously consume a lot of compute resource and would take a long time. Now, the technique of ray tracing was actually created as a solution to this problem. So to show how ray tracing works, we need to rearrange our pinhole camera slightly. So we swap around the pinhole and the back screen like so. Now, we consider the screen, which is now in the middle of course, as a thin sheet that our rays can pass through. And instead of casting rays from the light source and hoping that they will end up going in the right direction to end up in the camera, we cast rays from the camera. Notice that the rays start at the position of the pinhole. The rays pass out through the screen and into the scene. When the ray strikes an object in the scene, we stop, and now we cast a new ray in the direction of the light source. We can then calculate how much light is striking the object at this point, and so we can calculate what the colour of the object at this point is. We can then plot a pixel on the screen at the location where the ray passed through it of that colour. And we can then repeat that with one ray for every pixel until we have a complete image. That is the basic process of ray tracing, and this is what we're going to be implementing in this project. There are all sorts of ways of making this better and more complicated, but they, as I say, introduce more complexity, so for now we're going to stick with building just a basic ray tracer. Okay, so that's a very brief introduction to how ray tracing works, and that is, as I said, what we're going to be implementing. We're not going to be looking at anything more sophisticated like path tracing or photon mapping or anything like that, at least not as part of this series. I might do an additional series later on where we go on to look at more advanced things like that. Okay, but for now, I suggest that we jump in and let's start with having a look at how we're actually going to arrange our code. And we'll start with building up a very simple SDL2 app that displays a window, and then we're going to extend that to display a basic image. Okay, let's jump to that now. Okay, so I'm here at my terminal window. I'm using Linux, so I tend to do things from the command line and using just a plain text editor. If you're using a different environment, you can definitely follow along using an integrated development environment or IDE like Visual Studio. That shouldn't present any problems. When I come to talk about make files and using gmake, though, those will not be relevant to you if you're using an IDE, because the IDE will take care of that for you. Okay. The only other thing to mention is if you're using Visual Studio, you should start a new project as a, I think, Windows terminal app or something similar to that, rather than a Windows app. It's been a long time since I've used Visual Studio, so I'm not sure I remember exactly. Anyway, so apart from the SDL2 library, we are only using the standard libraries for C++, and also, as I mentioned, the linear algebra library that I've developed as part of my YouTube channel before, which is on GitHub. So everything is as cross-platform as it could be. SDL2 is very good in terms of cross-platform support, so that shouldn't present any issues either. Okay, so let's start. So I'm just in my terminal, and I've gone and created a new folder into which we're going to put the code. You can see that at the moment it is completely empty, which is where we would expect to start. So what we're going to do is we're going to start creating some files. The first file we're going to create is going to be called capp.h. So what we're going to do is just open up a text editor, and we're going to have a look at that. Okay, so here in our text editor, we're going to start with our code. And the first thing we do, because this is the header file for capp, so capp is going to be the sort of main code of our application, which is going to handle the window and all of that kind of thing. The first thing we're going to do is declare some include guards. So we have if fndef capp.h. So that is a compiler directive. It's simply an instruction to the compiler, and it says that if capp.h is not defined, then we want to define capp.h like so, and then we end up with an indif at the end of our code. And the reason we do that is that if this include file ends up being included multiple times, the compiler has a way of knowing that it's seen it before, and it doesn't need to go through the process of compiling it multiple times, so that can be quite efficient. We're then going to bring in SDL2, so hash include SDL2/SDL.h, like so. And remember, as I said, follow the instructions from the SDL2 website on how to install that for your particular system. Okay, we're now going to create a class for our app. So we have class CApp, like so. And remember the semicolon at the end of the curly braces for a class in C++. And within our class, we're going to have a number of public methods. So declare those. So we have public. We have, first of all, the constructor for our class itself that accepts no inputs. We have an on execute method that will return an integer, accepts no inputs. We have bool on init, like so, and void on event, which accepts a variable, a pointer to an SDL event object, like so. We have void on loop, like so, and void on render. I will explain the function of all of these when we come to actually write the code, and void on exit, like that. And now we have a bunch of private stuff, it's member variables and so on. So really just the things to start with for SDL2. So let's just call that SDL2 stuff. So this is the stuff that's going to allow SDL2 to really work. So we have a variable of type boolean called isRunning, like so. And we then need a pointer to an SDL window object that we're going to call pWindow, and a pointer to SDL renderer object, which we're going to call pRenderer. Okay, and that is actually everything that we need for the header file for capp.h. So let's go and have a look at how we put together capp.cpp, which is of course the main code for the application. Okay, so in capp.cpp, first thing we need to do, of course, is hash include our capp.h file that we've just created, and we're then going to define the default constructor for our class. It's called the default because it accepts no inputs. Let's save that, there we go. And capp capp, like so. And in here we're just going to simply set our initial variable. So we have isRunning is true initially, pWindow is set to null, and pRenderer we also set to null. Okay, and that's it. That's everything we need for the constructor. We're not bothering to declare a destructor. That possibly we should do that, but I think the exit code is handled elsewhere, so we don't need to worry about that. Okay, so now let's define the rest of our methods. We have bool on init, like so. Okay, so this is simply going to handle initialization of SDL2 and set up the window and everything like that. Alright, so first of all we want to call SDL init from the SDL library, which will handle the initialization, and we want to initialize everything like that. If that returns less than 0, then we know something has gone wrong, so we return false. Okay, otherwise we can assume that everything has initialized as it should. We now define our window, so pWindow we set equal to SDL create window, just like that, and we're going to call it QB ray tracer. Forget to subscribe. Okay, and we need SDL window pars centered. That just means to put it in the center of the screen in terms of width and height. So we do that for both of those. We want to make it 1280 by 720 and SDL window shown, just like that. Okay. Now, what we're going to look at now is we're actually going to initialize the window, so we need to configure it and everything else. So we need, most importantly, we need to create the renderer. So if pWindow is not equal to null, so if the process above was successful, then we are going to create our renderer. So pRenderer is equal to SDL create renderer pWindow -1 and 0. Those are just standard things. I'm not an expert with SDL2. I'd be the first to admit that. So, you know, some of this has really just come from the SDL2 documentation, and I don't necessarily know what all of it does. So the -1 and the 0 there, I must confess I'm not sure, but it works, so we stick with it. If our p window is still equal to null, which means our process has failed, then we return false. Otherwise, we come down to here and we simply return true, and that's the end of that function. Alright, so the next one is on execute. This is going to be called when we initially set up the app. So it's int on execute, like so. So within here, we need to create an SDL event object, which we're calling event, or pointer to an SDL event. We're going to call the onInit function here. Okay, so we have if onInit, like that, is equal to false. That means if the initialization fails, we return -1. Okay. Otherwise, we set up our loop. So the way any kind of app like this works is that we establish a loop that runs all the time while the window is open, while the code is running, and so we simply have a while loop that runs while isRunning is true. Remember, we defined isRunning already. We're then going to handle events. We need to do that so the user can close the window when they've finished with it. So we use SDL poll event ampersand event. So we pass the reference to our event object. If that is not equal to 0, okay, so while SDL poll event is not equal to 0, we call our onEvent method and we pass the reference to the event object. Okay, so that handles events. We're going to come to onEvent in a moment. We then call our onLoop function and our onRender function, and that is the end of our loop. So you can see what happens there. So while isRunning remains true, this block of code is simply going to run continuously, and it's going to loop through any events that it can find that are returned by SDL poll event, and it will call the onEvent function that we're going to write in a moment for each one of them. Okay, and once the loop has finished, it then calls onLoop and then calls onRender, and then it simply loops around again. So it will continuously run the contents of this while loop. Okay, right. So the next thing we need to look at is our onEvent function. Right, I'm just going to create some lines down here. There we go, make it a little bit easier to see what's going on. Okay, so we have void capp code colon. Did I get that right everywhere? No, that should be a double colon. Apologies. And there, of course. I think I hadn't never written in C++ before. Anyway, capp colon onEvent, and this accepts an input of a pointer to an SDL event, like so. And we're only interested in one type of event at the moment. So if event type is equal to SDL quit, like so, we set isRunning to false. Okay, and you remember in the loop here, this loops continuously while isRunning is true, so anything that sets isRunning to false is simply going to cause this loop to stop. Okay, and that will then be when we want to exit our program. That is everything that we need to do to handle events. We then have capp onLoop, so this gets called every time through our loop. For now, we don't have any code in there at all. And then we have capp onRender, which also gets called every time through our loop. Okay, and in here we are going to do stuff. We are going to set the background color to white, like so. We do that with SDL set render draw color p renderer, like so, and 255, 255, 255, which is red, green, and blue, and alpha. Okay, so that's white, and then we use SDL render clear p renderer, like that. And finally, we actually need to show the result to update the window. Okay, show the result, which we do with SDL render present p renderer. Okay, and that's everything for render. And the one final thing that we need is to handle exit. So we have void capp on exit, like that. Okay, so what we're going to do here is tidy up SDL2 stuff. Okay, so we use SDL destroy renderer, p renderer, like that, SDL destroy window, okay, p window, set p window, oops, if I can spell, p window equals null, and we call SDL quit, that then finishes everything off. And that is all of the code that we need in capp.cpp. Okay, so it simply defines an onInit function that initializes everything. We have onExecute that we call initially to make the app run. We have our loop that loops continuously while the app is running. We have onEvent, which only interprets the event of type SDL quit, in which case it sets is running to false, which will make this loop finish and then drop out of onExecute. Okay, right. So as it stands, of course, we haven't defined an entry point or anything like that. So this code on its own isn't really going to do anything. We need to create one more code file, which we're going to call main.cpp, which is going to actually make the app work. So let's have a look at that now. Okay, so main.cpp is very simple. We only have to hash include capp.h, like so. Okay, and then we simply declare int main, so this is the entry point for our code, int arg c, this is the standard C plus char star arg v, like so. Okay, and within there, all we need to do is we declare an instance of our capp class, so capp the app, simply like that, and then we return the app.on execute, which will run the execute function, and that's it. Now, if we go back to our terminal window, if we look at what we have, we now see that we have the code there that we've just created. So now we're in a position we can actually try compiling this to see if it works. If you're following along on an IDE, you should just be able to run it. That should be straightforward. It should take care of that for you, depending on what system you're using. For me, I use G++ from the command line. I'm going to specify -o. We're going to create an executable called QBRay, and we are going to compile main.cpp and capp.cpp, and we need -l SDL2 to bring in the SDL2 library, -std equals C++ 17. That's yes, that's what I meant. A small c there. Yeah, apologies. Okay, and we run that. Okay, and if we now look, we see that we have our QBRay executable, and we can run /QBRay, and it comes up on my other screen, but if I swoosh that over here, we see that we get our white window now with a QBRay tracer and our don't forget to subscribe subtle hint title. Okay, so that's the basic structure that we're going to use for our ray tracing code. Everything else we're going to do is going to sort of fit into this so that we can display a ray traced image in this window. Now, we're not going to look at it actually implementing any ray tracing today. We've got a few episodes to go through before we get to that. But what I want to do at least is create something so we have some kind of image in this window that's a bit more interesting than just the white screen. Before we can talk about that, though, I want to talk about how I'm going to structure the code for the whole project in total. So let's have a look at that now. All right, so just close that. Now, what we're going to do is, so I'm going to use gmake for running my builds. Now, if you're following with an IDE, as I said, you can skip this bit, really. You don't need to worry about that. The one thing that you should do, though, is we're going to create a subfolder within our code directory, which we're going to call QBRaytrace. Okay? So if I now do that, you can see we now have that folder here. Okay? And in there, we're going to put all of our other code that we're going to use. So we keep everything nice and separate. So we have our main entry point code and the capp code here. And then essentially all the library code that actually implements the ray tracing is going to go into the QBRaytrace folder or directory. Before we do that, though, I want to create what's known as a makefile. Now, a makefile is the list of instructions that tell gmake how to actually manage the build for our project. So let's have a look at that now. Okay, so I'm just in my text editor again. I've created a file that's simply called makefile. No extension, literally just makefile. And the first thing we're going to do is define the link target. Save that, there we go. So we define link target equals QBRay. Okay, now this isn't C++, this is the language for gmake that we're using here. So link target is essentially the name of the executable that we want to create. So as we just did with the manual compiling when I used G++ from the command line, we created an executable called QBRay, and that's exactly what we want to do here. Now, we can also define the libraries that we need. Okay, so we know that we need SDL2, so we have libs equals -l SDL2. Okay. Define any flags that we want to use for our compiling. So we want C flags, and we have one, which is -std equals C++ 17, a small c, as we just learned. Okay. All right. Now we're going to define the object files that we need to use. So when C++ compiles code, it first compiles each C++ for each .cpp file is compiled into an object file, a .o extension, and then the linker goes through and puts all of those together to create the final executable. So in order to manage our build, we need to first define exactly which object files that we're going to be using. So we simply create a variable called objects, and we need main.o for main.cpp, and the slash there is just for a new line. I just want to tab that out so I can put these neatly. There we go. And we have obviously capp.o because we have capp.cpp. Now, rather than having to list every individual CPP file that we have, that is one way that we could do it. We could just go through here and we could add an entry, a .o name here for every CPP file that we create. Now the problem with doing that, of course, is that we would then have to do that every time we created a new file. We'd have to go into our makefile and we would have to change it. Now I don't think that's really the best way to do it, and luckily there is a way that we can get gmake to scan our subfolder individually. Okay, so automatically for any new files that have been created. So let's look at that now. What we're going to do, and this starts to look a little bit complicated, but we do $pat subst, which I assume stands for pattern substitute, and we want to replace anything that has a .pp extension with a .o extension. Okay, and we have then a comma $wildcard /qbraytrace, that's the subfolder we just created, /star.cpp. Okay, close bracket and close bracket. So what that's going to do is scan through the qbraytrace directory, finding any files with a .cpp extension, okay, which it then detects here, and it will substitute anything with .cpp to whatever that was, .o. So it will create entries in the objects variable similar to the ones we created there by hand, but the difference being it will do it automatically, which is pretty cool. Okay, so next we need to define the rebuildables. So these are the files or things that can be rebuilt every time we want to run our build. So we define rebuildables like that is equal to objects, so we $objects and $link target. Okay, so rebuildables is simply everything that's defined here in objects and what we defined here in link target. Okay, the order is important, right? And now what we're going to do is define two rules that actually manage the build. Okay, so we define our first rule, so the rule to actually perform the build. Now this is a little bit confusing. The first rule is actually the one that will run last. Okay, they run in reverse order. So the first rule we're doing is actually going to be the instruction to perform the linking that will link all of the object files together. So we do $link target like so, colon, $objects. Okay. So that's the name of the rule, and within that command to run is g++ -g -o $link target. So that gives us the -o QBRay that we used before when we did this by hand, and $objects. Okay, $objects next, and then we also want to pass instructions for any libraries. So we have $libs, and finally our flags, flags. Okay, so that will instruct the linker to run, and it will put together all the object files and C flags. There we go. Right, and it will then add the commands that we put in for the libraries and for the C flags as well. Okay, now the second rule, okay, this is the rule to create the .o or object files. Okay, now it is a bit confusing. The second rule does actually get executed first. So what's going to happen is the second rule will run, so every time we come to this any object, so for every object in objects, it will run rule 2, so it'll go through all of the objects running rule 2 and then we'll go back to rule 1. Okay, so this is going to do ascent.o, okay, ascent.cpp, just like that, and this is actually going to do the compiling. So you have g++ -o, and slightly strange syntax. We do $ampersand like that, which is then going to read all of the entries in the objects variable. I don't understand exactly how it does that, but it does, so we just go with it. -c $less than symbol, okay, and then we have $c flags like that, because we want to use the flags when we do our compiling. Okay, and that's actually everything that we need. Those are the two rules, pretty much everything. One last thing we do is we create .phony, and we create a new instruction called clean, which does rm $rebuildables. Now the point of that is it simply means we can run make clean as a command, and it will remove all the rebuildables, which can be very useful. Alright, so let's save that. So we've simply saved that as makefile, nothing else, it's just makefile on its own. And so if we look at that in our folder, we can see now we have here makefile. And now what's cool, in order to compile our code, we only have to run make, just like that, and that will go through. And indeed you can see how it works. So this is rule 2 that has run for main.cpp, and then it's run rule 2 for capp.cpp, and then that's all of the cpp files we have, because there's nothing in here yet. So then it runs rule 1, which actually then goes through and performs the final linking. And let's just run that just to make sure it did indeed work correctly. And there we go. Okay. Alright, so that probably seems a lot of work to achieve very little, but believe me, as we go and add more and more files to our project, that's really going to be important and worthwhile. So trust me on that one. Okay, so finally we're just going to look to create a very simple image in our window, not using ray tracing, but I want to finish with something a little bit interesting. So we're going to create a class to handle images, which we're going to call QBImage, and that's going to form the bedrock really of our ray tracing code in terms of image handling. So let's have a look at that now. Okay, so I've gone ahead and created a new file in our QBRaytrace directory that we just created, which is called qbimage.hpp. Okay, and we simply do as before, if ndef, we define our include guards, we always do this, hash define qbimage h, okay, hash ndef. So I explained the functionality of that before, I'm not going to cover it again. Okay, so this is qbimage.hpp, and we will go on to look at qbimage.cpp in a moment. But first of all, let's flesh this out. We need some includes. We need to bring in string. I'm not actually sure that we use that at the moment, but we will do perhaps in the future. We bring in vector, so those are just from the standard library. And of course, we have to hash include SDL2/SDL.h, like so. And we then declare our class. This is QBImage, like so. Remember the semicolon after the last curly brace for a class in C++, very easy to forget, causes no end of problems. And we're going to define the default constructor. Okay, now we don't necessarily need to do that because the compiler could take care of that for us, but it may be more useful in the future, so it's worth doing anyway. So we simply QBImage like that, and we have a destructor for this one, okay, which is tilde QBImage like that, and then we need a function to initialize our image. So we have void initialize with a z, okay, and this accepts as input constant x size, constant y size. It's obviously the size of our image, and an SDL pointer to an SDL renderer object, which we're going to call sp renderer. Okay, that's initialize. We then need a function to set the color of a pixel. That's an obvious one, really, isn't it? Since we need to be able to do something with our image. Okay, so that's also going to be void set pixel, like that. Const int x, const int y, that's the x and y location of the pixel we want to change. And this is going to perhaps look a little bit odd. We're going to define colors just using doubles. Const double red, const double green, and const double blue. Okay, like that. Okay, so that's everything. Now, people that may remember the previous series I did on this, I spent a lot of time then developing a class to handle color. I'm not going to do that this time, and also we're going to store our colors using double precision floating points. And now the reason that we're doing that will become obvious when we go on to later episodes, particularly when we come to look at lighting and shading and that sort of thing. But just for now, just roll with it. We're storing colors as doubles. It does, of course, mean we have to convert them when we want to use them in some way. But that's not a big deal. And there is a big payoff to it, which you will see in later episodes. So we need a function to return the image or display. Okay, so void display. Actually, it doesn't return the image, but it will handle displaying it. And then we have a bunch of private stuff. So we have, oh right, okay, see, I forgot. These are all the public methods. That's my fault, sorry. Just tab those out. Okay, like so. And we have some private things. Okay, so we have private functions first. We have a function that returns a uint32, and this is convert color. Const double red, const double green, and const double blue. So the function of that is it accepts the three RGBs as double precision floating points, and it will return a single uint32 that represents that in normal 8-bit color space, 8-bit per channel color space, or 24-bit color space that we can then use for SDL2. And we have void init texture, that's to handle some SDL2 stuff. We'll talk about that in a moment. And we then have some private variables as well. We need arrays to store the image data. Okay, so I'm going to store the image data simply using vectors from the standard library. Okay, so there are different ways you can handle multi-dimensional, or in this case two-dimensional, of course, arrays in C++, but I quite like to do it this way. So we do std vector of type std vector of type double. So that is a vector of vectors of doubles, if you see what I mean. And mr channel is obviously the red channel data, and we do the same std vector double mg channel, okay, and std vector double mb channel, like that. So obviously those are our red, green and blue channels respectively, right? We then need to store some various other things. We need to store the dimensions of the image, store the dimensions of the image like so. So we just have int m x size and m y size. That's pretty straightforward. And then we have some SDL2 stuff that we need to store as well. We need to store our pointer to the renderer, mp renderer, and we also need to store a texture. We're going to create and store a texture that we're going to use. We'll see how that works momentarily. P texture, like so. And save that. Okay, and that's what we need. That's the qbimage.hpp file. So let's have a look at how we would put together the Cpp file for this now. So the Cpp file, first of all, obviously we hash include qbimage.hpp that we've just defined, and I'm going to leave that out. Okay, so the first thing we're going to do is define our default constructor. Okay, qbimage : qbimage, like that. And this is simply going to initialize things, so x size to 0, my size to 0, and m_p texture to null. Okay, we then have to define a destructor for this to make sure we tidy everything up properly. So we have a destructor, qbimage : tilde QB image like that. Now, if m_p texture is not equal to null, then we want to destroy it. So we use SDL destroy texture m_p texture, just like that. Okay, it's pretty straightforward. So the point of declaring when we construct a class, our image class, we force m_p texture to point to null, and then that means that if we then call the destructor before anything happens, we don't then throw a segmentation fault or anything like that, because we detect, before we try to destroy it, we detect whether it's actually been defined or not. Okay. So next is our function to initialize. Okay, so this is void QB image : initialize, like so, const int x size, const int y size, and SDL renderer star p renderer. Okay, like so. No, no semicolon there, obviously. So first thing we're going to do, resize the image arrays. So we have mr channel dot resize x size, and then std : vector type double y size 0.0. Okay. G channel, this is the same, dot resize x size std vector double y size 0.0, and of course B channel is also going to be exactly the same, std vector double y size 0.0, just like that. Okay, we're going to store the dimensions. Okay, so m_x size equals x size, m_y size equals y size. So we store our dimensions, and we store the pointer to the renderer. Okay, m_p renderer equals p renderer. That's easy. And we need to initialize the texture. Okay, we just call the init texture function that we're going to define in a moment. Okay, and that's what we need our function to initialize. So let's just put some lines in there so you can see what's going on more easily. And we're then going to declare our function to set pixels. Okay, function to set pixels. Okay, so we have void QB image : set pixel const int x, const int y. It's obviously the x and y locations, and then we have const double red, const double green, and const double blue, like so. And we simply set the pixels. That's easy. So we do m_r channel dot at x dot at y equals red, and I think you can see where this is going to go. m_green channel at x dot at y equals green, and mb channel dot at x dot at y equals blue, just like that. And that's what we need to set a pixel. Pretty straightforward. We then have a function to generate the display. Okay, so this will actually cause it to display the image to our renderer that's been specified. So we have void QB image : display, accepts no input parameters. We're going to allocate memory for a pixel buffer. Now, memory for a pixel buffer, like that. Now, the reason we're doing this is we're going to, it's convenient to create a simple array of uint32s to act as a pixel buffer, and we're going to modify the values of that, and then we're going to use that to create our texture. So uint32 star temp pixels equals new uint32, and this is going to be a size mx size multiplied by my size. So it's a one-dimensional array of uint32s of size x size times y size. Okay. We then clear the pixel buffer, right, that we've created, and we do that using memset temp pixels 0, the value we want to write to it, m underscore x size multiplied by m underscore y size multiplied by size of u int 32. Okay, that's that. And so now we just need to loop through our SDD vector channels. So we've got m red channel, m green channel, and m blue channel stored as SDD vectors. We need to go through those, and we need to generate a uint32 for each pixel and store that here. So we simply do that with for int x equals 0, x less than m x size plus x, like so. And then obviously another loop, int y equals 0, y less than m y size, semicolon plus y. Okay, now this probably could be made faster by rearranging the order of the loops, but you know, we're not aiming for real time anyway, so I think we'll just stick with that. So then we do temp pixels, that's our pixel buffer, at we have y multiplied by m underscore x size, like so, plus x. Okay, so that simply converts our two-dimensional x and y coordinate to a linear index into temp pixels. And then that's going to be equal to convert color, which we're going to write in a moment, mr channel at x at y, mg channel dot at x dot at y, and mb channel dot at x dot at y. Okay, just that. Semicolon, and we finish our loops. We've done that already. Alright, so after we've done that, that will populate our pixel buffer with the color data that we want. We then need to update the texture with the pixel buffer. Okay, so we use SDL update texture m underscore p texture, that's the pointer to the texture, null temp pixels, okay, that's the pixel buffer, and mx size multiplied by size of uint 32, and that's what we need to actually just update the texture. And now we're going to delete the pixel buffer because we finished with it. Okay, very important if you use the new keyword anywhere in C to remember that you have to delete stuff. And I know that in modern C++ terms, you know, using new and stuff is not really recommended, but SDL2 is of course written in C, so we have to be compatible with that. So we do end up with this slight mixture of C++ and C, but I really don't have a problem with that personally, so yeah, just go with that. And then, so that's defined our texture. We've deleted our pixel buffer. The final thing we have to do is copy the texture to the renderer, okay? So we define an SDL rect object called source rect and bound. So we have two. So then we do source rect.x. Help if I could spell, wouldn't it? Source rect.x is equal to 0. Source rect.y is equal to 0. And source rect.width is equal to 1280. And source rect.height equals 720. Now, you'll notice there's a limitation there. Those are hard-coded. Really, they should be picked up, you know, when we initialize everything. Yeah, m underscore x size and m underscore y size, just like that. That's better. Okay, and then we have bounds is equal to source rect. So we have two rectangles there, exactly the same, and then we just use SDL render copy mp renderer, okay, and mp texture. So that's going to copy the texture into the renderer. Source rect defines where in the texture we want to copy from. We want the whole texture. And bounds is where we're going to copy to, ampersand. Reference to bounds, like so. Okay, that's it. So that is everything for the function to generate the display. So now we need code for initializing the texture and converting the color. So we're going to tackle initializing the texture first. Here we go. So function to return the image as an SDL2 texture. Function to actually initialize the texture. Okay, like that. So this is void qb image : init texture, just like that. So initialize the texture, uint32, rmask, gmask, bmask, and amask. Okay, we're going to define those. Now we have a compiler directive here, so we need to know whether we're using big endian encoding or not. So we have if SDL underscore byte order equals SDL underscore big endian. In that case, we configure rmask. And in fact, in order to get these right, I am going to copy and paste this block of code because I don't want to make a mistake, and it would be really boring for you to watch me just debugging stuff. Okay, so paste that in. So this has come from the SDL2 documentation. Okay, so if in the case that we're using big endian encoding, we define our masks this way, otherwise we define them that way. Okay, right, so we then need to delete any previously created texture, right? So if m underscore p texture is not equal to null, then we bracket like that, then we do SDL destroy texture m underscore p texture, just like that. And we're going to create the texture that will actually store the image, which is, so we do SDL surface star temp surface, so we create a temporary surface from which we're going to create the textures. SDL create RGB surface 0 m underscore x size, m underscore y size, 32, because it's 32 bits per pixel, r mask, g mask, b mask, and a mask, just like that. Okay. And m underscore p texture then, to create our texture, is equal to SDL create texture from surface, so you can see how that works, based on our renderer, so m underscore p renderer and temp surface, just like so. And then we don't need the surface anymore, so we use SDL free surface temp surface, just like that. Okay, and that's everything we need to initialize. And now we need our function to convert colors to uint32. This is fairly simple, and we're nearly there, I promise. So uint32 qbimage : convert color, and this accepts as input const double red, const double green, const double blue, just like that. Okay, first of all, we convert the colors to unsigned integers. Right, so unsigned char r is equal to static cast to unsigned char red, unsigned char green is equal to static cast unsigned char green, just like that. Unsigned char b static cast unsigned char blue, like so. And then we use the compiler directive again for the big endian order, so hash if SDL byte order equals SDL big endian. We define our color as uint32 pixel color is equal to b, and these are the bit shift operator, b shifted by 24 bits, g shifted by 16 bits, and e shifted by 8 bits, plus 255, because we're an alpha of 255. Otherwise, we define pixel color as 255 shifted by 24, that's the alpha, and then red shifted by 16, and then green shifted by 8, and finally plus b. Okay, hash end, and then finally return hash end if, right, and finally return pixel color. Okay, and save that. Right, so that is everything. That's qbimage.cpp and qbimage.h. So then obviously the important thing is to make sure that that code compiles without errors, and because we went through the effort of making our make file, we can just run make in our main folder, and it picks that up, and okay, we have an error there on line 8. Let's have a look at that. Indeed, yes, obviously that should be a semicolon. Right, let's go back, try again. Source rect was not declared in the scope. That's line 73. 73, yep, of course. Source rect, capital R. Save, back, make. And finally, uint32. Okay, yep, on line 117. Okay, there's some fairly schoolboy errors. Easy to do. Okay, so hopefully that should fix it. Okay, so we see that our code still compiles and it still runs, and of course it still does exactly the same thing. So we're going to change that now. We actually want to do something a little bit more interesting. Right, so to do that, we need to go back to our capp.cpp. Actually, first of all, back to capp.h. Okay. Okay, so in capp.h, the only thing we need to change is we need to include the file that we've just created. So it's ./qbraytrace. That's the folder we put it in at qbimage.hpp. Okay, so we include that, and we want to declare an instance of that. So we're going to declare it as private. This is going to be an instance of qbimage class to store the image. Okay, qbimage m_image. Just like that. Okay, now let's look at what we need to do in capp.cpp. So in capp.cpp, we want to initialize our image when we call the onInit function. So inside here, where if p_window is not equal to null, we initialize the renderer. Okay, and then we're going to here initialize the qbimage instance. Okay, so here we call m_image dot initialize and 1280 by 720, that's the dimensions we're using, and we pass the pointer to the renderer. Okay, and because we don't want to update it every frame as we loop through that, we're simply going to create an image here. So to make it interesting, create some color variations. Right, so we're going to do for int x equals 0, x less than semicolon x less than 1280 plus x, and for int y equals 0, y less than 720 plus y. Okay, and I'm going to declare a variable double red is equal to static cast double x divided by 1280.0 multiplied by 255. Okay, and we're going to do double green is equal to something similar, static cast to double y divided by 720 multiplied by 255.0. That should be 255.0 there. Okay, and then we just do image dot set pixel x, y, red, green, and 0.0. Okay, that's pretty straightforward. Now, if we were to run that as it is, it still won't do anything, and the reason for that is that we haven't actually told anything how to actually handle rendering our image. So if we go down to the onRender method here, so between the bit we have the blocker code that sets the color to white, and then we have the show result, and here we are going to display the image, and all we have to do is image dot display. Okay, and that should be everything. Now if we go back to our terminal, we should be able to compile that, and now when we run QBRay, oh, it still doesn't do anything. Ooh, right, okay. After taking a bit of a debugging break there, I did find what the problem was. And if we look back at the problem was in qimage.cpp, qbimage.cpp, and I had specified these wrong. So this is uint32. So we are down here in the convert color method or function, and we have r bit shifted by 24, g by 16, b by 8, and 255, and there I'd also made a mistake there as well. Okay, so fixing those, saving that, and back to our terminal window. If we run make, okay, and QBRay, there we go. And that's it. There's the actual final image that we get. Okay, so that's really everything that I want to talk about today. I think that's really quite enough for one episode. We've gone through the basics of how we set up an SDL2 app, so we can create a window, and we've gone on to create the QB image class that we're going to use as part of the ray tracer to actually handle our image data. And we've produced a mildly interesting image on our window. Now, that may not seem a lot. We've spent a lot of time, we've written a lot of code, and we haven't really got anywhere, but we will, in the next episode, move on to talk about more specific ray tracing things. So the next episode is going to focus on the camera geometry and the camera class, and then from there we should be able to move on and hopefully start actually looking at ray tracing fairly soon. Anyway, listen, I really hope you've enjoyed that. It's been a great deal of pleasure making this video, so if you have liked it, please do remember to hit that like button, and if you haven't done so already, please consider subscribing to my channel so that you don't have to miss any future videos, especially the next episode, as I say, when we're going to start talking about the camera class and camera geometry. Anyway, listen, it's been a pleasure. I really hope you've enjoyed it, and I really hope you found it useful. Do let me know in the comments below, and yeah, and I really look forward to seeing you in the next video. Thank you very much for watching. Bye.